The largest machine humanity has ever built is the electrical grid. It is a sprawling, interconnected web where power generation and human demand must match perfectly, down to the absolute millisecond. Every catastrophic failure starts with something mundane: a tree branch brushing a conductor, or a single lightning strike hitting a high-voltage transmission line in the countryside. Let's freeze time at the exact point of impact. From the moment that bolt connects, the continent has exactly 1/10 of a second to save itself before plunging into total darkness. Whether our hospitals keep running or our city shut down depends on an invisible, automated war fought inside that microscopic fraction of a second. At 0.001 seconds, the physics of a fault take over. A short circuit drops the voltage on a specific line to zero, creating an electrical vacuum that rips current from its path, pulling massive energy toward a single exit point. Standard generators are forced to push out current exceeding 20 times their normal output, shoving a tidal wave of energy into the breach. By 0.06 seconds, the grid's protection relays intervene. These are decentralized digital brains that sample current and voltage hundreds of times a second to detect these exact anomalies. These relays act like a reflex arc, similar to the way your hand jerks away from a hot stove. Before a human could even blink, the relay sends a command that forces giant circuit breakers to physically trip, amputating the damaged section of the line in just 60 milliseconds. This self-amputation stops the surge, but severing a major power artery creates an immediate system-wide imbalance between supply and demand. This imbalance causes the grid's frequency to plummet. Frequency, measured in hertz, tracks how many times alternating current changes direction each second. At 0.09 seconds, the rhythm is dropping rapidly below its required 50 or 60 hertz baseline. To prevent a collapse, the grid relies on inertia. Traditional power stations generate electricity using 100-ton steel rotors spinning continuously inside these massive turbine casings. Because these heavy rotors are already in motion, they naturally resist slowing down. As frequency dips, they sacrifice spinning speed, converting their stored kinetic energy into a brief burst of emergency power to hold the system together. The kinetic energy spinning inside the British grid alone carries the same momentum as 10,000 high-speed trains. This kinetic buffer buys time, but if the frequency falls below 49 Hz, individual power plants will trip offline to protect their own machinery, triggering an unstoppable cascade. Our most advanced electrical network survives this crucial 1/10 of a second due to the primitive momentum of heavy spinning metal. Time resumes past that first 1/10 of a second. The lights flicker, but they hold. However, the mechanical safety net that just saved the grid is currently being dismantled. Unlike coal or nuclear plants, solar arrays and wind farms do not rely on hundreds of tons of synchronized spinning steel. As we transition to renewable energy, these physical counterweights vanish. The grid's overall inertia is shrinking, which means frequency collapses can happen much faster, making the entire network more fragile. To stabilize the future grid, engineers are deploying grid-forming inverters. An inverter is a device that converts direct current from solar panels into the alternating current used by the main grid. These specific units use high-speed algorithms to act as virtual inertia, injecting power in microseconds without relying on physical mass. Decarbonizing the world's energy supply involves replacing millions of tons of spinning steel with lightning-fast code, balancing humanity's greatest machine on the very edge of physics.